Hi, my name is Nazzatul Hanaa Binti Mohamad Kamal. My matric number is 221401012. And the title for my project is The Effect of Different Outlet Diameter and Length to Diameter Ratio on the Velocity and Pressure Distribution of the Water Jet Nozzle. For the introduction, I will explain about the problem background. The image in the slide is the nozzle that I use for the analysis simulation. I'm sure that we're familiar with water jet nozzle. This is because this product is widely used in industry for cutting, cleaning, and surface preparation. However, understanding the behavior of fluid flow within this system can be complex, requiring advanced tools. Based on the problem that I mentioned before, there are two objectives identified from it. First, to apply the CFD method in the result analysis and visualization. This is because CFD method provide realistic conditions such as material properties and boundary conditions that help to predict how different design choice affect system performance. Second objective is to investigate the impact of varying key parameters such as outlet diameter in mm and length to diameter ratio on the velocity and pressure distribution within the jet nozzle. As I mentioned before, the project focused on two key design parameters. First is outlet diameter and second is length to diameter ratio. Outlet diameter is equal to the size of the opening through which the water exits the nozzle, and there are three different diameter, which is 2 mm, 3 mm, and 4 mm. For length to diameter ratio, it refers to the ratio between the length of the outer and the diameter of the outlet's hole. And the parameter I choose is 2 to 1, 3 to 1, and 4 to 1. The dependent parameter in the study are velocity and pressure distribution. Why I choose velocity? Because velocity indicates how the speed of the water varies across the track, which directly impact the efficiency of the system. Second is pressure, because pressure helps to understand how the force from the jet is applied along its length and affect the interaction with the target surface. Here are the step-by-step procedures undertaken to simulate and analyze the flow in the nozzle using computer-aided engineering tools. Starting from creating phase group, mesh generation, servo setting, turbulence, transport properties, boundary condition, and monitoring. Here I will explain a bit detail about the procedure. After import the geometry, I will split the geometry to allow the assignment of specific boundary condition. There are two phase group that I select. The first is at the top, and I identify it as inlet to allow fluid to enter the system. And the second phase is at the bottom, and I name it an outlet, defining the region where the fluid is exists. This setup is important to allow for proper configuration of the flow boundaries during the simulation process. In mesh generation step, geometry for the nozzle was enabled in order to ensure proper meshing of of the model. Next, at the base step, the geometry was set to outer size to allow the bounding box to fit the visible geometries automatically. Last, for material point, since the default location was already inside the flow, then the material point was set to 000. After the mesh being generated, we need to check either the mesh is in good quality or not. To check the quality, we need to check the number of node and ensure it did not exceed 200,000. Also, at the skewness, aspect ratio, and non-orthogonality. As we can see here, all the summary here is in good quality. Next, in the setup panel, the steady state option was chosen as the flow through the nozzle is constant over the time. The flow was set to incompressible since water velocity and pressure condition do not significantly affect its density. Also, in the turbulent panel, Run's modeling was chosen. In the boundary condition panel, the inlet was set as inlet velocity. A velocity of 5 meter per second was assigned, which is the speed of the water entering the nozzle. Then the outlet was set as a pressure outlet with the pressure value at zero, representing atmospheric pressure. This ensures the water flow out the nozzle under the correct pressure condition. To monitoring the result, a slice was created at axis Y to visualize the flow characteristic. In the field list, both velocity and pressure were selected to simulate and record this result. The table presents the result of the mesh independence analysis, showing the velocity values and percent deviation of different mesh division. This analysis was conducted to identify the optimal mesh size that balance accuracy and computational efficiency. As you can see here, division for 40, 30, and 70 is selected in terms of low percent of deviation, which is 1.85% and lesser computational time. The smaller the deviation, the closer the simulation results are to conversion. This division used 34,752 elements, which is considerably smaller than the division for 50, 40, and 70 with 50,838 elements. It is because finer mesh require more elements, which increase the computational time and memory usage. Each show that these mesh divisions strike a balance between accuracy and computational cost. Here is the result for outlet diameter. As we can see at the table, a smaller outlet diameter result in a higher maximum velocity. From the table, we can see when the diameter become larger from 2 mm to 4 mm, the maximum velocity become less, which from 298.91 meter per second to 102.41 meter per second. This result create a graph that illustrates inverse relationship. This aligns with the principle of continuity, which state that the mass flow rate must remain constant in a steady, incompressible flow. From the slide, we can see the formula for mass flow rate equal to rho AV, which rho means fluid density, A is cross-sectional area, and V is velocity. This means if the fluid mass flow rate and density are constant, it will give the constant formula as AV. This means cross-sectional area and velocity are inversely proportional. As the diameter decrease, the cross-sectional area decrease. So the fluid velocity must increase to maintain the same mass flow rate. Uh, Same with the result for velocity versus pressure. Since the velocity decrease, kinetic energy also will decrease. To maintain constant total energy, pressure energy must increase. And along with the Bernoulli principle, which in a steady incompressible flow, the total energy in a flowing fluid is constant. This means velocity and pressure are inversely proportional. So when the diameter increase, velocity will decrease, reducing kinetic energy to balance the total energy, and the pressure energy must increase. Here the color contour plot for the outlet diameter result. As we know, the red region representing high velocity. From the color contour plot, we can see the high velocity are intense at 2 mm diameter. As the diameter increase, The red region spread out and become less intense, meaning the velocity is lower. This makes sense because when the pipe gets wider, the fluid has more space to move, so it slows down. This is exactly what the principle of continuity predicts. Similar with velocity, similar with velocity, uh, the red region representing high pressure are also most intense at the 2 diameter. As the diameter increase, the red region also spread out and become less intense. This region decrease in intensity and spread out with increasing outlet diameter. This is linked to Bernoulli principle, which says that if the fluid slow down like it does when the pipe get wider, the pressure should increase. So from the result, we can see the plot perfectly demonstrate how this fluid mechanic principle work together. Here the result for second parameter, which is length to diameter ratio. Uh, Based on the result in the table, we can see minimal variation in maximum velocity and pressure. Same goes to the graph. It shows that both velocity and pressure change in a non-linear way as the length to diameter ratio increase. Initially, both decrease slightly. Beyond a certain point, both start to increase again. This suggests that length to diameter ratio has a less pronounced effect compared to outlet diameter. As we can see, impact for short nozzle, velocity slightly decreased from 164.26 meter per second to 163.58 meter per second. The pressure also decreased slightly alongside velocity. This is because in a nozzle, fluid need time to adjust to the geometry and reach its maximum velocity, and short nozzle cut this process short, resulting in less efficient acceleration. Next, impact of longer nozzle. We can observe that velocity increased slightly to 165.69 meter per second, and pressure also increased to 15,709 Pascal at 4 to 1 ratio. This is because in a longer nozzle, the flow has more. And here is the result for color contour plot. As we can see, the color contour plot are different at different ratio, show minimal variation. Similar pattern indicate that change in the length to diameter ratio had a negligible impact for flow characteristic with the test range. This suggests that other factors such as nozzle geometry or inlet flow condition might play more significant role in influence fluid behavior. Here the summary of the project. Firstly, the objective that successfully achieved by applying CFD method to analyze the effect of outlet diameter and length to diameter ratio on the water jet velocity and pressure distribution. The result for analysis show that outlet diameter significantly impact the velocity and pressure, while length to diameter ratio change had minimal effect, as reflected by similar color contour plot. Also, by refining the mesh, the accuracy and reliability of the simulation result can be ensured through a quick independent study. Next, the finding of the project that give insight how different design choice affect system performance. Also, contribute to a better understanding of the factor influence flow behavior in water jet system. To deeper the understanding of water jet system performance, I recommend to explore the influence of other key parameters such as nozzle geometry and inlet flow condition. And that's all from me. Thank you.